Welcome to Physcribe. This opening deck builds a single idea that lets a whole system of particles behave like one point. The idea is the center of mass. By the end of these slides, you will know how to locate the center of mass for many particles and for the special case of two particles. You will see how velocity, acceleration, and Newton's second law look when written for the system as a whole, using m a cm equals F external. You will also recognize four properties that make the center of mass a robust modeling tool. It is independent of the motion of the particles. For a rigid body, it is fixed relative to the body. It may lie outside the body. And for a symmetric, homogeneous body, it coincides with the geometric center. Hold on to a through line for the rest of the course. Translational quantities like mass, momentum, and kinetic energy all live at the center of mass. Rotational quantities like moment of inertia, angular momentum, and torque all live about an axis. Keep those two addresses straight, and rotational mechanics stops feeling like a new subject. So what is the center of mass physically? It is a single point with two useful properties. First, the whole mass of the system can be imagined as concentrated at that point when we study translational motion. Second, every external force on the system can be imagined as acting at that point when we write Newton's second law for the system. For a rigid body, the center of mass is fixed relative to the body. Picture a thrown hammer, a spinning top, or a gymnast in midair. The center of mass glides on a smooth parabola while the body tumbles around it. Think of the center of mass as the address of the whole system for translation. Now for the general formula for the center of mass. Take a system of n particles with masses m1, m2 up to mn, located at position vectors Ri. The position vector of the center of mass, rcm, is m1 r1 plus m2 r2, and so on, all divided by the total mass m1 plus m2 and so forth. Equivalently, using summation notation, it is the sum from I equals 1 to n of mi ri, divided by the sum from I equals 1 to n of mi. In words, read this as an average of positions weighted by mass. In Cartesian components, each coordinate independently follows the exact same weighted pattern. For example, the x-coordinate of the center of mass is the sum of mixi over the sum of mi, and the identical form holds for the y and z coordinates. Notice that the dimensions of each evaluated coordinate are still simply length, because dividing by the total mass leaves the original position units intact. Finally, a highly useful intuition to keep in mind. Heavier masses will always pull the center of mass closer towards themselves. Let us apply that to the simplest case, a two-particle system. Place two masses, m1 and m2, separated by a distance d along a line. Call the position of m1.0 and the position of m2.p. Measured from m1, the center of mass is at a distance r1, given by m2 times d divided by m1 plus m2. Measured from m2, the center of mass is at a distance r2, given by m1 times d divided by m1 plus m2. Add the two expressions and you get back d as you should. A quick limiting check. If m1 is much greater than m2, then r1 tends to 0 and r2 tends to d. The center of mass sticks to the heavier mass. If the two masses are equal, the center of mass sits exactly halfway between them. Sanity checks like these will keep reappearing throughout rotational mechanics. Now place the same two particles in a coordinate plane. Pick an origin O and draw position vectors r1 and r2 to the two particles. The center of mass position vector is m1 r1 plus m2 r2 divided by m1 plus m2. The diagram shows an important subtlety. The resultant vector rcm does not point to the midpoint of r1 and r2. It is a mass-weighted resultant. The point lies on the segment joining the two masses, but is closer to whichever one has more mass. The same idea generalizes to many particles by simply adding more terms to the sum. Differentiate the center of mass definition with respect to time, and you get the velocity and acceleration of the center of mass. Vcm is the sum of mivi divided by the sum of mi, and a cm is the sum of mi divided by the sum of mi. The linear momentum of the whole system is therefore P equals m times Vcm. Newton's second law for the whole system reads F external equals dP over dt, which equals m times a cm. For an isolated system where F external is 0, the center of mass moves with constant velocity. If it started at rest, it stays at rest. If it was already moving, it glides forever. Internal forces like pushes, pulls, and even explosions cannot move the center of mass. Four properties are worth keeping in mind. First, the center of mass is a point computed from masses and positions. It need not lie inside the object. Think of a ring, a hollow sphere, or a boomerang. Second, its position depends on the shape, size, and mass distribution of the body. Third, for a homogeneous symmetric body, such as a uniform rod, a square, a circle, a sphere, or a cube, the center of mass coincides with the geometric center. Fourth, in pure translation, the center of mass moves with the body, while in pure rotation, the center of mass stays where it is and the body turns around it. The takeaway is this. When you study any complicated motion, whether a wrench spinning in zero gravity, a diver off a board, or a planet plus its moon, translate the dynamics to the center of mass, and the translational part reduces to a single particle problem. In the next slide package, we apply the very same center of mass idea to angular quantities. A rigid body preserves the distances between all its constituent particles. Its general motion is the superposition of two simpler pieces, a translation of the center of mass and a rotation about some axis through, or through a point fixed relative to, the center of mass. Before we can describe that rotation, we need rotational variables and rotational equations of motion, the right-hand rule analog of position, velocity, and acceleration. In the next slides, we will meet the rigid body idealization itself, the definition of pure translation and pure rotation, the three kinematic equations for constant angular acceleration, and the rotational counterpart of mass, which is the moment of inertia. A body is said to be rigid when it has a perfectly definite shape and size. The distance between any two particles of the body does not change, no matter what forces are applied. In this idealization, the interparticle bonds are infinitely stiff. Any real body is only approximately rigid. A steel beam is closer to the ideal than a rubber rope, but both are treated as rigid whenever the deformations are negligibly small. Within a rigid body, we can classify every motion as translation, where every particle has the same displacement in a given time, as rotation, where particles move on circles whose centers lie on a common axis, or as a combination of the two. Let us contrast the two limiting motions. In pure translation, every particle of the body undergoes the same displacement in the same direction during a given interval of time. Different particles may carry different velocities only instantaneously if the body is also rotating. But for pure translation, the velocity field is uniform across the body. In pure rotation, each particle moves on a circle, and the centers of all those circles lie on a single straight line called the axis of rotation. Particles on the axis are at rest. Particles off the axis sweep equal angles in equal times. The general motion of a rigid body is just translation of the center of mass plus rotation about an axis through the center of mass. Now the language of rotation. Angular displacement theta is the angle swept, measured in radians so that arc length s equals r theta. Angular velocity omega equals d theta over dt, which is the rate of change of angle. Angular acceleration alpha equals d omega over dt, which also equals the second derivative of theta with respect to time. The associated linear speed of a particle at distance r from the axis is v equals r omega. The tangential acceleration is r alpha, and the centripetal acceleration is r omega squared. By convention, angular quantities are vectors whose direction is fixed by the right-hand rule. Curl the fingers along the rotation, and the thumb gives the direction of omega and alpha, and later of torque and angular momentum. For constant angular acceleration alpha, the rotational kinematic equations are formally identical to the linear ones. Replace s by theta, v by omega, and a by alpha, and you get the rotational set. The first equation is omega equals omega 0 plus alpha t. The angular velocity changes linearly in time. The second equation is theta equals omega 0 t plus 1/2 alpha t squared. Angular displacement is the initial rate times time, plus half of the rate of change times t squared. The third equation is omega squared equals omega 0 squared plus 2 alpha theta. Angular velocity squared grows linearly with angle. Pick whichever form eliminates the unknown you are not given. Here is the vocabulary bridge between linear and rotational mechanics. Displacement s maps to theta, velocity v maps to omega, acceleration a maps to alpha, mass m maps to moment of inertia I. Momentum p equals mv maps to angular momentum L equals I omega. Force F maps to torque tau. Newton's second law, F equals ma maps to tau equals I alpha. Kinetic energy 1/2 mv squared maps to 1/2 I omega squared. When a derivation feels stuck, write the linear version you already know and swap each symbol for its rotational partner. The next three decks build out the right column, moment of inertia, torque, and angular momentum, and then bring them together to handle rolling. Mass is the property by which a body opposes a change in its state of linear motion. The analogous property for rotation is the moment of inertia, written I for a body made of discrete particles of masses mi at perpendicular distances ri from the axis of rotation. I is the sum of mi ri squared. The picture shows three-point masses m1, m2, m3, sitting at horizontal distances r1, r2, r3 from a vertical axis of rotation, with a curved arrow indicating counterclockwise spin. The physical meaning is exactly the same as mass in linear motion. The larger the moment of inertia, the harder it is to change the angular velocity omega. The SI unit is kilogram meter squared, and the dimensions are ml squared. The moment of inertia about a chosen axis depends on four things: the position of the axis, such as the center of mass axis versus an arbitrary parallel axis; the orientation of the axis. For example, a long rod's eye about its perpendicular bisector is ml squared over 12, but about its longitudinal axis it is essentially zero. The shape and size of the body, and the distribution of mass relative to the axis. It does not depend on the angular velocity omega or the angular acceleration alpha. It does not depend on the material or color of the body. And it does not depend on the strength of the applied torque, so long as the body remains rigid. Here is a handy mental rule. Move mass away from the axis and I grows as r squared, so spreading mass far from the axis costs you rotational agility. The radius of gyration k of a body about an axis is the root mean square distance of its constituent particles from that axis. It is the square root of the average of r1 squared, r2 squared, and so on taken over n particles. Because the moment of inertia is the sum of mi ri squared, and that equals m times the average of ri squared, we have the clean relation I equals mk squared, or equivalently k equals the square root of I over m. The radius of gyration is not a geometric radius. It is an effective distance such that, if every particle of mass m were placed at k from the axis, the moment of inertia would be reproduced. Its SI unit is the meter. A quick limiting check. For a single point mass at distance r from the axis, k equals r. The parallel axes theorem says that for any rigid body of mass m, the moment of inertia about any axis equals ICM plus mr squared. Here ICM is the moment of inertia about a parallel axis through the center of mass, and r is the perpendicular distance between the two axes. The diagram shows an irregular body with its center of mass labeled, and two parallel vertical axes drawn through it, one through the center of mass and another offset by a perpendicular distance r. The reading is straightforward. The further you shift the axis from the center of mass, the larger I becomes always. The minimum I for a given orientation is the center of mass value, and I grows quadratically with the offset. The theorem applies to any rigid body, two-dimensional or three-dimensional. The perpendicular axes theorem applies only to planar laminas, that is, two-dimensional bodies lying in the xy plane. For such a body, Iz equals Ix plus Iy, where Ix and Iy are the moments of inertia about two mutually perpendicular axes lying in the plane of the body, and Iz is the moment of inertia about a third axis through the same point, perpendicular to the plane. The diagram shows a lamina in the xy plane, with Ix and Iy in the plane through the origin O, and Iz perpendicular to that plane through the same point O. A common trap is forgetting that this theorem holds only for laminar planar bodies. For a three-dimensional body, you must use the sum of mi ri squared directly or break it into laminae first. Together, the two axis theorems let you compute I for any axis, once you know one center of mass result plus the geometry. We begin our catalog of standard bodies with a thin circular ring of mass m and radius r first. For an axis through the center and perpendicular to the plane, the moment of inertia I is mr squared. Second, for a tangent axis perpendicular to the plane, we use the parallel axis theorem with a shift of r, giving it equals mr squared plus mr squared, which is 2mr squared. Third, about a diameter, symmetry tells us that Ix equals Iy, so using the perpendicular axis theorem, Iz equals Ix plus Iy, which equals 2Ix. This means the diametral moment of inertia ID is 1/2 mr squared. Fourth, for a tangent axis lying in the plane of the ring, we apply the parallel axis theorem to get it equals id plus mr squared, which yields 3/2 mr squared. Finally, look out for a common trap. Since every mass element of a thin ring is located at the exact same distance r from the central axis, its moment of inertia is exactly mr squared, not 1/2 mr squared as you would find for a solid disk. Now the solid circular disk of mass m and radius r for the axis through the center, perpendicular to the plane, I equals 1/2 mr squared. For a tangent axis perpendicular to the plane, add mr squared to the central result, giving it equals 3/2 mr squared. About a diameter, id equals 1/4 mr squared. For a tangent axis lying in the plane of the disk, the same recipe gives it equals 1/4 mr squared plus mr squared, which is 5/4 mr squared. Here is a consistency check. The disk has less material at the rim than a ring of the same mass and radius, so the moment of inertia of the disk, 1/2 mr squared, is strictly less than that of the ring, mr squared. That ordering is exactly what we expect. 3 more standard shapes. For a thin rod of mass m and length l, the moment of inertia about a perpendicular axis through the center is ml squared over 12. About a perpendicular axis through one end, using I equals ICM plus mr squared with r equal to l over 2, the result is ml squared over 12 plus m times l squared over 4, which is ml squared over 3. For a solid cylinder of mass m, length l, and radius r, the moment of inertia about its central longitudinal axis is mr squared over 2, and about a parallel axis through the outer face it is 3/2 mr squared. About a perpendicular axis through the center, it is ml squared over 12 plus mr squared over 4. And through a diameter of one circular face, it is ml squared over 3 plus mr squared over 4. For a rectangular plate of mass m with sides L and B, the moment of inertia about a perpendicular axis through the center is m times L squared plus B squared divided by 12. A note worth keeping. The cylinder's longitudinal I does not depend on L at all. Only the disc-like cross-section enters, which is why long shafts feel easy to spin. The last pair of standard shapes. For a solid sphere of mass m and radius r, the moment of inertia about any diameter is 2/5 mr squared, because the sphere is isotropic. About a tangent, add mr squared to get 7/5 mr squared. For a thin spherical shell of mass m and radius r, the moment of inertia about any diameter is 2/3 mr squared, and about a tangent it is 5/3 mr squared. Here is the comparison insight. For the same m and r, the order from smallest to largest moment of inertia is solid sphere, then spherical shell, then disk, then thin ring. The reason is that the mass gets pushed further and further from the center in that sequence. A solid sphere is therefore the easiest of the lot to spin up, and a thin ring is the hardest. The torque, also called the moment of force, of a force F about a point is the cross product of the position vector r from that point to the line of action of the force, with F itself. So tau equals r cross F, which equals rf sine theta times a unit vector n perpendicular to the plane of r and F. The direction of n is given by the right-hand rule. Torque is a vector quantity. Its SI unit is the Newton meter, and its dimensions are m L squared t to the minus 2. The sign convention we will use throughout mechanics is anticlockwise positive and clockwise negative. Torque is also called the moment of force, or a couple when it is produced by a pair of equal and opposite forces with parallel lines of action. 2 limiting cases are worth memorizing. When sine theta equals 1, the force is perpendicular to r, which is the lever arm configuration where torque is maximum. When sine theta equals 0, the force points along r, so pushing straight at the pivot produces no twist at all. Just as F equals ma is the bridge between linear force and linear acceleration, the bridge between angular acceleration and force is tau equals I alpha. It is a vector equation, with both tau and alpha along the axis of rotation chosen by the right-hand rule, and I is the moment of inertia about that axis. The reading is direct. Doubling the moment of inertia halves the angular acceleration produced by the same torque, which is exactly the rotational sluggishness intuition. Doubling the torque doubles the alpha. This single equation lets us treat wheels, pulleys, and rotating shafts by the same recipe as point masses. The angular momentum of a particle of linear momentum, mv, about a point is L equals r cross mv, for a rigid body rotating about a fixed axis with moment of inertia I and angular velocity omega. The angular momentum is L equals I omega. Vectorially, L equals I omega along the axis, with the direction set by the right-hand rule. The SI unit is the joule second, which is the same as kilogram meter squared per second, and the dimensions are m L squared t to the minus 1. Like torque, angular momentum is meaningful only with respect to a chosen point or axis. Differentiate L equals I omega with respect to time, and you get dL over dt equals tau external. This is the rotational form of Newton's second law for a system. Two powerful consequences follow. First, the principle of moments, which is rotational equilibrium. If a body is in rotational equilibrium, then the sum of tau I equals 0 around any point, with clockwise torques taken as negative and anticlockwise as positive. Second, conservation of angular momentum. If tau external equals 0 on a system, then L equals I omega stays constant, so I1 omega 1 equals I2 omega 2. If I decreases, as when a skater pulls in her arms, then omega must increase so that L is unchanged. That is why a pirouetting dancer speeds up by hugging the body, why a diver tucks, and why a helicopter needs its tail rotor to keep the total angular momentum balanced against the main blades. A rigid body is in equilibrium when both its linear momentum and angular momentum do not change with time. This means there is no linear or angular acceleration, so the sum of external forces is 0, and the sum of external torques is 0. These two vector equations give us 6 scalar equations in 3 dimensions, or 3 in 2 dimensions, forming the basis for solving classic statics problems like a beam on 2 supports, a leaning ladder, a crane lifting a load, or a sign hanging from a single bolt. Next, a couple is defined as a pair of equal and opposite forces acting along parallel lines. A couple produces pure rotation with no net force, but creates a torque of magnitude F times d, where d is the perpendicular separation between the forces. We see couples at work in steering wheels, screwdrivers, and tap keys. Finally, a common trap in these problems is confusing torque with force, since torque already has the lever arm R built into it. The center of gravity of a body is the point at which the gravitational torque about that point is 0. For uniform gravity, where g is constant across the body, the center of gravity coincides exactly with the center of mass. For very large bodies such as planets, oceans, or stars, where g varies measurably, the 2 points separate. Angular impulse is the time-integrated effect of a torque, and it equals the change in angular momentum. So J equals the integral of tau dt, which equals delta L, which equals Lf minus Li. A short, large torque, such as a cricketer's bat striking the ball or a racket string snapping back, delivers the same change in L as a smaller, longer torque, as long as the integral over time matches. Angular impulse is the rotational analog of linear impulse, where the integral of f dt equals delta p. Take this idea into the next deck. Torque, angular momentum, and angular impulse let us write the rotational analogues of every useful linear result, and the next deck layers rotational energy on top of those laws to handle rolling bodies. A spinning body stores kinetic energy in every particle. Adding the kinetic energies of all the mass elements gives the rotational kinetic energy k rot equals 1/2 I omega squared. The formula is directly analogous to 1/2 mv squared. Replace m by I and v by omega. The SI unit is the joule, a useful reading. Doubling omega quadruples k rot, so a child's top spinning twice as fast carries 4 times the energy. Doubling I, for example, by adding mass at the rim, only doubles it. The same expression can be derived as the sum over particles of 1/2 m I v I squared equals 1/2 I omega squared. The parallel axis theorem recasts this into 1/2 mv squared plus 1/2 I cm omega squared when the body has both translation and rotation, which we will see in the next slides. A torque tau acting through an angular displacement d theta does work tau d theta. Total work over a path is W equals the integral from theta 1 to theta 2 of tau d theta. For a constant torque, this simplifies to W equals tau times theta 2 minus theta 1, which is tau times the angle moved. The corresponding power delivered by the torque is P equals tau omega. These match the linear versions W equals the integral of f dx, W equals F times S, and P equals Fv once you swap displacement for angle and force for torque. A practical use. A motor of fixed torque driving a wheel at higher speed delivers more mechanical power. An engine's torque curve and the gearbox together pin down the operating point. A wheel of radius r rolling without slipping on a level surface obeys the rolling constraint Vcm equals r omega. The instantaneous velocity of the contact point on the wheel is 0, so the wheel is not skidding at the contact. The picture of combined translation and rotation makes this vivid. The top point of the wheel moves at 2v to the right, the center moves at v, and the bottom point is instantaneously at rest. For comparison, pure rotation about a fixed axis gives v equals r omega in opposite senses at the top and bottom, while pure translation gives every point the same linear velocity v to the right. The instantaneous axis of rotation of a rolling wheel is the contact line, which is at rest even though the wheel's center is moving. A rolling body possesses both translational and rotational kinetic energy. The total kinetic energy, K, equals 1/2 mv squared plus 1/2 I omega squared. By substituting the moment of inertia using the radius of gyration, K, and the rolling constraint, omega equals v over r. This simplifies to 1/2 mv squared times the quantity, 1 plus k squared over r squared. For a body of mass m rolling down an incline of angle theta, its linear acceleration down the slope is given by a equals mg sine theta divided by m plus I over r squared, which reduces to g sine theta over 1 plus k squared over r squared. The speed at the bottom is v bottom, equal to the square root of 2gh over 1 plus k squared over r squared, where the height h equals s sine theta. The time taken to cover the distance s is t, equal to the square root of 2s times 1 plus k squared over r squared, all divided by g sine theta. As a helpful tip, notice how the rotational inertia acts like extra mass in the denominator, dragging the acceleration down without changing the gravitational force available. For bodies of the same m and r rolling down the same incline, the smaller k squared over r squared, that is, the smaller I, the bigger a, and the bigger v bottom. The order of finish, fastest first, is solid sphere, then disk or cylinder, then spherical shell, then thin ring. For rolling without slipping, the minimum coefficient of friction required is mu min equals F over R, which equals I over R squared times A, all over mg cosine theta. Here F is the friction force at the contact patch, R is the normal reaction, and A is the actual rolling acceleration. If the available friction is below this minimum, the body skids instead of rolling. As takeaways, translation lives at the center of mass and rotation lives about an axis. Keep both addresses straight. The rotational toolbox mirrors the linear one with theta to s, omega to v, alpha to a, I to m, tau to f, and L to p. Moment of inertia is a geometry of shape, axis, and mass distribution. And the parallel and perpendicular axis theorems extend one known I to every orientation. Torque, angular momentum, and the conservation law I omega equals constant organize any spinning system. Rolling without slipping combines translation and rotation through the single constraint VCM equals R omega, and the body's I sets how much of the gravitational energy goes to spin. Common traps to avoid. Confusing torque with force since torque has the lever arm R built in. Applying the perpendicular axis theorem to three-dimensional bodies because it is for laminar two-dimensional bodies only. Forgetting that the minimum mu depends on cosine theta, so flatter slopes need less friction to roll without slipping. Any problem where an object is constrained to rotate, from gears and pulleys to planets orbiting the sun and electrons in a magnetic field, becomes tractable once you write the rotational Newton's second law tau net equals I alpha and use the linear constraint at the right places. This concludes the Physcribe introduction to rotational motion, covering center of mass, moments of inertia, torque, angular momentum, equilibrium, and rolling. The next Physcribe video applies these tools to angular collisions, gyroscopes, and rotational stability. Like, share, and subscribe to keep the rotation going.